Welcome to the last installment of comparing linear and exponential functions. And in this video, we're going to focus on examining written descriptions or verbal descriptions of functions and determining whether or not they represent linear or exponential contexts. And from the context, we're going to come up with an equation, and that will allow us to make predictions based on what's happening. So let's take a look at some key differences between a linear and an exponential context. Okay, so in a linear description, what we see happening is it's a situation where we are talking about an increase or a decrease by a specific quantity over a specific time, or maybe a different unit other than time. So it's increasing or decreasing by a specific number. So here's a couple of examples of this. GGC's freshman class increases by about 212 students per year. We can kind of make a prediction based on, well, about 212 more students each year register for classes in the freshman class. Notice that this doesn't change at all. It's like a constant rate each year, 212 students per year. Or here's a decreased one, because linear functions can increase or decrease. The amount of toilet paper in a store decreases by about 200 rolls per hour. Okay, again, this is a specific quantity over a specific amount of time. Now, when we're talking about exponential descriptions, that's a little bit different, because instead of talking about a specific quantity, we're talking about a specific percentage over a specific time or other unit. And so we'll see things like this happening. The cost of gas has increased by about 1.2% per month from 2001 through 2015. Now, notice this wasn't like 5 cents per gallon per month. It was 1.2% per month. Or the amount of bacteria in a Petri dish doubles every 5 hours. Now, you may say, how is that a percentage? Well, it's adding exactly 100% to what was there before, right? Doubling would be 200%. And so instead of adding a specific value, doubling represents a percentage. And so would tripling, or so would quadrupling, okay? So let's look at a couple of examples of these types of applications. Again, we got some words, so we want to slow down and read the words, all right? The population of a town is increasing by 2% each year. State whether this growth is linear or exponential. If the population is 1,100 today, what will the population be in about 4 years? Justify your answer with either an equation or a table. Okay, so the very first thing we want to know is this linear or exponential? Okay, so we know it's increasing, but that doesn't tell us anything. It could be either from that. The key element here is, how is it increasing? Is it increasing by a specific quantity or by a percentage? And we can see that it's increasing by a percentage, which tells us we have an exponential situation going on. Okay, so we know we've got something going on like this. Y is equal to A times B raised to the X. Now remember that in an exponential context, A, that vertical stretch or shrink, also represents the y-intercept, which, if we're talking about a function of time, which this is, we are going to say that that is our initial value, okay? And so our initial value of 1,100 goes in for the value of A. Now, this is important. To find the multiplier, we are interested in an increase of 2%, okay? So when we're talking about a multiplier and we are talking about percentage, what we're going to be doing is we're going to be taking 1 and adding or subtracting the percentage rate as a pure decimal to that value of 1. Now, why do we do that? Well, because that 1 represents 100%. And so if it's increasing, we would want something a little bit more than 100% or 102%. Okay, and if it's decreasing, we would say that the multiplier would be slightly less than 100%, like 0.97 or 0.75, depending on how it's decreasing. So if we're increasing or decreasing by a percentage, you're going to use this 1 plus or minus r thing for the multiplier. So we can say that our b value here is 1.02. So we can go ahead and fill in these elements in our equation, and now we have a function. F of x here is 1100 times 1.02 all raised to the x power. Okay, so now we want to predict what the population will be in 4 years. So we're going to take that 4, we're going to sub it in to our function wherever we see x here and here, and we're going to crunch this and find that the population is going to be about 1,191 people in that 4 years. Okay, so it's not a huge amount of change, but there is a significant amount of change, right? So that's almost 100 people. Okay, so now how would you justify this with a table? Well, with a table, you would have to show how that population is increasing year to year. So we would take a table and just fill in our populations each year. Now remember, if we start at 1,100, to get to the population after the first year, you would have to add 2%. So you could take 2% of 1,100 and add it, or you could just multiply 1,100 by 1.02. Okay, and again, you can take 2% of this value and add it, or you can multiply this by 1.02. And you can see that as you do this, you're going to end up with 1,191 people. So you can do it either with a table or with an equation, right? So last example here, the number of students at GGC is increasing by 610 people each year. State whether this growth is linear or exponential, and if the population is 12,150 today, what will the population be in 4 years? Justify your answer with either an equation or a table. So this is a similar context to what we saw before, except that when we're looking at the increase or decrease, we see we're increasing by a specific quantity every year, which tells us we're talking about a linear context. So then we can say, okay, we need to know the rate of change, the slope, and the initial value. So our initial value we know is 12,150. That's our y-intercept. Okay, and then if I'm dealing with the rate of change, it's increasing by 610 people per every 1 year. That's our rise over run, 610 over 1. And so our slope is 610. And so as I place these values in the correct positions in our equation, we end up with a function of f of x is equal to 610x plus 12,150. And then if I want to find the population in 4 years, again, we're going to take 4 and sub it in for our x value. And we would say f of 4 is equal to 610 times 4 plus 12,150. So we can crunch those numbers and expect that in about 4 years, the number of students at GGC would have increased to about 14,590. Now, similar to our exponential context, you could justify this with a table by starting at your initial value of 12,150 and increasing by 610 each year, and you would end up at the same place. All right, that wraps up comparing linear and exponential functions. I'll see you next time.